Namaskar and a very warm welcome to NCERT's live interactive program. I am Neha Tripathi. You are watching us on SWAYAM Prabha's channel Kishore Manch, and you can also watch us on our official YouTube channel NCERT Official. In this session, we are going to continue our session on polynomials for class 10. We have already discussed meaning and concepts in detail. We have learnt about the zeros of a polynomial, coefficients and its classification. Today, we will discuss more topics under this chapter, and we have with us Professor V.S. Prasad. He is Professor in Mathematics from Regional Institute of Education, Mysore. Welcome to the show, Prasad sir.
Thank you, madam. Good morning, viewers.
Good morning, sir. I'll just take a few seconds to inform our viewers that if you have any questions related to the topic, please call us on our toll-free numbers 1-800-111-265 and 1-800-111-2199. If you are watching us on our official YouTube channel NCERT Official, you can leave your questions in the comment section and you can mail your questions at ciet.kishoremanch@gmail.com. That's it. Sir, let's start this session. And if we can start, like we have learned about the zeros and the coefficients of polynomial, if we can start this session with their relations.
Yes. Thank you, madam. So today we are going to see whatever the things we learned in the last class, how to link all those things. In fact, in the last class, we have seen what do you mean by coefficients of a polynomial, what do you mean by zeros of a polynomial. Those are the things, and how to find all those things for a given polynomial. These are the things we already learned. In fact, today we are going to observe is there any interconnection between the coefficients of a given polynomial as well as the zeros of a polynomial. This is one of the most important concepts which helps us to find out lots of applications in the higher level also. So let us see today what are the things we are going to discuss. So in the first slide, we have listed like relation between zeros and coefficients of a linear polynomial, next quadratic polynomial, and maybe cubic polynomial, and in general we will observe that situation also. And similarly, problems based on the relation between zeros and coefficients of given polynomials, and also we will see division algorithm for polynomials with some examples. These are the things we are going to discuss. Yes, first let us see what is the relation between zeros and coefficients. You know already, coefficients of a polynomial means the corresponding constants of different variable and their powers of the variable given in the polynomial expression. And the zeros of a polynomial is, it is the value of a polynomial at which the value is equal to 0. These are the two things we have already seen actually. Now let us see what is the connection between 0 and the coefficients of given polynomial. First, let us observe for linear polynomial. This is one of the easiest case. So that's why first consider the linear polynomial. Suppose if you take a linear polynomial as p of x is equal to ax plus b with a not equal to 0, then we know that to find it 0, just by equating that equation ax plus b is equal to 0 and simplify that equation, we will get x is equal to minus b divided by a. Hence, if you use a new notation for 0, say alpha. So if alpha is a 0 of the linear polynomial ax plus b, then that alpha is nothing but minus b by a. This is the relation between the 0 and the coefficients of a linear polynomial, which is very easy to identify. For example, let us check this. Of course, generally, if alpha is a root, then it is related by minus b by a, where b is the constant term in the equation and a is the coefficient of x. This is the general notion to give the relation between 0 and the coefficients of a linear polynomial. For example, let us start to apply this for some examples. Consider a polynomial p of x is equal to 2x minus 1, which is a linear polynomial. Then its 0 can be found out by taking 2x minus 1 is equal to 0, and by simplifying this equation, we will get x is equal to 1 by 2. Hence, the 0 of p of x is equal to 1 by 2. 1 by 2 can be written as minus of minus 1 divided by 2. For our convenience, we are splitting like this, where minus 1 is the given coefficient in the given polynomial expression, and 2 is the coefficient of x. Therefore, it's satisfying the condition that zeros of p of x is equal to minus constant upon coefficient of x. Similarly, let us take one more example involving irrational number also. Let p of x is equal to cube root of 3 times x plus 9. Root of 3 x plus 9. Then to find it 0, you know already, but I am directly using the equation. So 0 of p of x is equal to, the relation is minus the constant term divided by coefficient of x. Here, whatever the coefficient constant we are taking, along with the sign we have to take. Here both are positive, there is no problem. So here the constant term is 9 and the coefficient of x is root 3, therefore minus 9 by root 3. Therefore, the 0 of p of x also satisfies minus 9 by root of 3. Like that, we can identify the relation between roots and coefficients for a linear polynomial. But the most important thing is how it works for the quadratic polynomial. Here, we will get some extra relations that we will see. Before going to see that relation, let us check it by taking one example first. So consider a quadratic polynomial given by p of x is equal to say 6x square minus 7x minus 3. Then by using their earlier knowledge, what we call it as method of splitting the middle term, we can solve this equation. Consider p of x is equal to 6x square minus 7x minus 3. Now we are going to split the middle term. Note that to split the middle term, what we are going to do is we are multiplying the coefficient of x square and the coefficient of constant, that you will get 18. Then you have to split 18 in such a way that the difference of sum exactly gives the middle term. Here I am splitting that 18 as plus 2 into minus 9. Therefore, the middle term can be splitted as 6x square plus 2x minus 9x minus 3. This they have learned in class 8-9 already. Now, from the first two term, I can take 2x as a common factor. Therefore, it can be written as 2x times 3x plus 1 minus, I can take 3 as a common factor in the remaining two terms. That again becomes minus 3 times 3x plus 1. Therefore, we will get two terms. One is 3x plus 1, another one is 2x minus 3. Therefore, our given polynomial can be written as a product of these two factors, and hence the value of that polynomial is 0 when 3x plus 1 is equal to 0 or 2x minus 3 is equal to 0. This gives the idea that when x is equal to minus 1 by 3 or x is equal to 3 by 2. So the zeros of p of x is equal to 6x square minus 7x minus 3 are minus 1 by 3 and 3 by 2. Now let us see the relation. Suppose if I take the sum of those two zeros. First 0 is minus 1 by 3, second 0 is 3 by 2. So if I take minus 1 by 3 plus 3 by 2, then that becomes, they know how to take by taking the LCM of the denominator. The LCM is 6. Therefore, by clearing all those things, you will get the value 7 by 6. Again, as a notion, we are writing 7 as minus times minus 7 because our coefficient has a minus sign that we have to find out. Therefore, this expression gives the idea that minus coefficient of x divided by coefficient of x squared. This is the relation it satisfies. Similarly, if you take the product of those two zeros, that is minus 1 by 3 times 3 by 2. If you multiply these two things, you will get minus 3 divided by 6, where minus 3 is the given constant of the given polynomial and 6 is the coefficient of x squared. Therefore, this product also satisfying the condition constant divided by coefficient of x squared. That shows that there are two relations are possible for a given quadratic equation. Let us consider one more quadratic polynomial to make it very clear. Say p of x is equal to 4x square minus 4x plus 1. Again, by using the splitting the middle term, I am writing it as minus 4x as minus 2x, which comes by taking the product of the coefficient of x square and the constant term. 4 into 1 is 4 and split that 4 into minus 2 times into minus 2 times. So that shows that 4x square minus 2x plus 1. By taking the common factor from the first two terms as 2x, you will get 2x times 2x minus 1. And next term minus 1 as a common factor, that also gives minus 1 times 2x minus 1. That means this polynomial has again two factors, which is a repeated factor, 2x minus 1 times 2x minus 1. Therefore, the value of p of x is 0 when we take any one term as 0, that is x is equal to 1 by 2. That means the values of p of x are 1 by 2 and 1 by 2 repeated 2 times. Then if you take the sum of these two zeros, that is 1 by 2 plus 1 by 2, that gives 1. Now as a notion, by observing the coefficients of the given polynomial, this 1 can be written as 4 by 4 and numerator 4 can be written as minus times minus 4. Therefore, minus times minus 4 divided by 4 exactly indicates minus times the coefficient of x divided by coefficient of x squared. And similarly, if you take the product of these two zeros, 1 by 2 times 1 by 2 gives 1 by 4, where 1 is the constant term in the given polynomial and 4 is the coefficient of x squared. That shows that every time when you consider a quadratic polynomial, in general, if now I am going to use two words, say alpha and beta. These are the two Greek words actually. So for our purpose, we are using these two as indicating as zeros of a quadratic polynomial. So if alpha and beta are the zeros of a quadratic polynomial of p of x is equal to ax square plus bx plus c with a not equal to 0, then We know that since alpha is a 0 means by using our 9th class factor theorem, x minus alpha becomes a factor. Similarly, if beta is a 0, then x minus beta becomes a 0 of that factor. Therefore, x minus alpha and x minus beta are the factors of that polynomial p of x. Now, we are going to express our polynomial p of x as ax squared plus bx plus c is equal to some constant multiple of those factors, because sometimes some common factors may come. That's why the general notion is whenever we have two factors, then along with the product of those two factors, let us take one constant, say k, a real number, which gives the general representation of the given polynomial. Now, when we expand this factor x minus alpha into x minus beta, we will see that k times x square minus alpha plus b times x plus alpha beta, that is nothing but kx square minus k times alpha plus beta of x plus k alpha beta. I am multiplying k inside the bracket. Then by comparing the coefficients and constant terms on both sides, we will see that a is nothing but k, b is equal to minus k times alpha plus beta, and c is equal to k times alpha into beta. This gives alpha plus beta can be written as b minus b divided by k, means minus b by a, where a is equal to k, and alpha into beta is equal to k alpha beta divided by a, means k gets cancelled, c divided by a. That means the general notion is sum of those two zeros exactly satisfying the relation as minus the coefficient of x divided by the coefficient of x square. Similarly, the product of zeros, that is alpha into beta, can be generally represented as constant term divided by coefficient of x square. With these examples and general notations, we can observe that these two are the relations between zeros and coefficients of a quadratic polynomial p of x is equal to ax square plus bx plus c with a not equal to 0. Suppose, let us see some problem by using this. In fact, last time one student asked, when we have 0 and root 5, how actually the corresponding equation looks like. Actually here 0 and root 5 are the sum and product of the given zeros of the given problem. That is the change actually they have to observe. Now let us see this problem. Find a quadratic polynomial if the sum and the product of that polynomial is given as of those zeros as 0 and root 5 respectively. That means sum of the zeros is equal to 0 and product of the zeros is equal to root 5. These are the two things they have given. Now let us see how to apply this actually. Let us consider the general quadratic polynomial be ax square plus bx plus c, where a not equal to 0 of course, and let us assume that the zeros are say alpha and beta. Then it is given that the sum of the roots, that is alpha plus beta, is equal to 0, and by our relation it is nothing but minus b by a. And similarly the product of the roots b alpha into beta is equal to given as root 5, which is nothing but c by a. Now we got two relations. Now everything is in our hand. By taking one value as a is equal to 1, then I can easily see that b by a is equal to 0 and a is equal to 1 means b must be equal to 0, and c by a is equal to root 5 and a is equal to 1 means c is equal to root 5. So by taking a is equal to 1, I can easily identify the value of b is equal to 0 and c is equal to root 5. That shows that the one of the quadratic polynomial which fits the given condition b, x square plus root 5. We can check that any other quadratic polynomial that fits these conditions will be of the form k times x square plus root 5, where k is a real. So in this way, by observing the relation between roots and coefficients, we can also find out the given polynomial also. Let us try it for one more problem. For example, find a quadratic polynomial whose sum and product of the zeros are given by minus 1 by 4 and 1 by 4 respectively. Let us take the general quadratic polynomial be ax square plus bx plus c, and its zeros, let us assume that the zeros are alpha and beta. Now let us use the given condition, the sum of the zeros. If alpha and beta are zeros, then the sum alpha plus beta becomes minus 1 by 4 plus 1 by 4. Therefore minus 1 by 4 actually is given as sum of the roots. Therefore that you can write it as minus 1 by 4, which is equal to minus b by a, and the product of the roots alpha into beta is given as 1 by 4, that is nothing but c by a. So that shows that by using this relation, by taking a is equal to 4 as a notion, we can see that value of b becomes 1 and the value of c becomes 1. That shows that the corresponding one of the quadratic polynomial which fits for the given condition is 4 times x square plus x plus 1. You can check that any other quadratic polynomial that fits in these conditions will be of the form k times 4x square plus x plus 1, where k is any real number. So in this way, by using the relations of quadratic polynomials with roots and coefficients, we can identify the required quadratic polynomial very easily. Now let us try.
So we have seen about linear polynomial, we have seen quadratic polynomial.
Yes.
Now it's turn for the cubic polynomials, I
Yeah,
believe.
we can't discuss more about cubic polynomial, which is slightly a difficult thing for our students. But at least by observing previous thing as a pattern, for a linear polynomial, we have one relation, we got it. For a quadratic polynomial, we are going to get two relations. Our common sense says that definitely we can expect the corresponding relations for a cubic polynomial must be 3. So what are those 3 things that we will observe one by one? Now, for a cubic polynomial, let us consider a general form of cubic polynomial. We can always write it as p of x is equal to ax cube plus bx square plus cx plus d with a not equal to 0. Now here I am using one more new word called gamma. Normally these are the words taken from Greek words. That's why don't worry about all those things, just a notation. So if alpha, beta and gamma, pronunciation is like this, alpha, beta and gamma are the zeros of the given polynomial, then the sum of the zeros, the first relation is given by add all the 3 roots, that is alpha plus beta plus gamma. This is defined as minus the coefficient of x square. Whatever the second term comes in that polynomial, that coefficient you have to take with the negative sign, divided by coefficient of x cube. The first term, x cube term is first. Whatever the coefficient with respect to x cube, that you have to take it as a denominator. So minus b by a means minus the coefficient of x square divided by coefficient of x cube. This is the first relation we are going to get as a generalization. Then the product of the zeros, that is alpha into beta into gamma, this says that minus the constant term. In the given polynomial, the constant term is d and the coefficient of x cube is 3. Minus extra comes in this case. Earlier case this minus was not there, but here we are going to get minus the constant term divided by coefficient of x cube. And one more relation, because we have 3 numbers, among 3 numbers, not only sum, not only product, we have one more possibility is there, sum of the product of the 2 roots taken 2 at a time, that is alpha beta plus beta gamma plus gamma alpha. That relation is also possible. Therefore here we are going to get one more new relation for cubic polynomial, which is alpha beta plus beta gamma plus gamma alpha, which is equal to c by a, where c is the coefficient of x and the coefficient of x cube. So we are using coefficient of x cube, x square, x and constant term. By using all those 4 terms, we are getting these 3 different relations as sum of the roots, product of the roots and sum of the product of the 2 roots taken 2 at a time. These 3 relations we are going to get. In this way, for a cubic polynomial, we are going to get 3 different relations between roots and coefficients. In fact,
sir, our students are just getting confused about what are these alpha, beta, gamma. As you already said, these are just notations.
Yeah,
but if you can please elaborate or explain.
Okay, I can't use ABC because ABC is already there in the coefficient. I want a new notation. If they want, they can use MN, something like that, but just only to make it different as a zeros, as a number. Alpha indicates one number, beta indicates one number, and gamma indicates one number. These are the zeros of that polynomial. Just for simplicity, for the presentation in a new way, we are going to use it, which is also used in their textbook also. That's why a common notation I am using it. Alpha always indicates one root of that polynomial. Beta indicates second root of that polynomial, and gamma indicates the third root for the cubic polynomial. And therefore, I am going to list it all those things in one single way actually. That means, if you observe that entire list, whatever the relations we got it, of course, if you want to check it for cubic polynomial, let us see one example. That makes very clear for them actually. For example, I am going to take one cubic polynomial given by p of x is equal to x cube minus 6x square plus 11x minus 6. Here I am not discussing about how to find the zeros of that polynomial. Fortunately, I am giving zeros directly for them. You can easily check that. If you put x is equal to 1, you will get p of 1 is equal to 0. If you put x is equal to 2, you will get p of 2 is equal to 0. If you put x is equal to 3, you will get p of 3 is equal to 0. That gives the guarantee that 1, 2 and 3 becomes the zeros of this particular polynomial p of x. I am giving zeros directly. Then let us see what is the relation they are going to get it at. Then observe that the sum of the zeros, alpha is the first root, beta is the second root, and gamma is the third root. So alpha plus beta plus gamma, if I take, it becomes 1 plus 2 plus 3, that is equal to 6. As a notion, I can write 6 as minus times minus 6 divided by 1, because my second coefficient is minus 6. I want that minus sign. That's why I have adjusted the sign. So that shows that the relation becomes minus the coefficient of x square, which is nothing but minus 6, divided by the coefficient of x cube, which is 1. And second relation is the product of zeros, that is 1 alpha into beta into gamma, that is 1 times 2 times 3, that becomes 6. 6 can be commonly written as 6 divided by 1. So it fits in our relation minus times minus 6 divided by 1. Therefore, the relation satisfies minus the constant term. Here also the constant term is minus 6 divided by the coefficient of x cube, which is nothing but 1. This is the second relation, also satisfies very clearly. And the third relation is sum of the product of two zeros taken two at a time. That is alpha beta plus beta gamma plus gamma alpha. That is 1 times 2 plus 2 times 3 plus 3 times 1. It gives 2 plus 6 plus 3, that is equal to 11. That means 11 can be written as 11 divided by 1. Again, it can be represented as coefficient of x, which is nothing but 11, divided by coefficient of x. Hence, all the relations are easily verified for this particular polynomial. In this way, we can see that the relations actually satisfies very clearly. In general, I would like to make a common statement for that one actually. For a linear polynomial, we have one relation. That is nothing but that root is equal to minus b by a. For quadratic polynomial, we have two relations. One is sum of the roots, that is alpha plus beta, that is nothing but minus the coefficient of x divided by coefficient of x square. And another one is product of the roots, that is alpha beta, that is nothing but constant term divided by coefficient of x square. And for cubic polynomial, we have three relations that we have already seen. Alpha plus beta plus gamma is equal to something, alpha into beta into gamma is equal to something, and alpha beta plus beta gamma plus gamma alpha is equal to something. These are the three relations we are going to get. And in general, we can see that a polynomial of degree n, we can find n different relations for the particular polynomial. So these are the ideas about relations and coefficients of a given polynomial. Any questions?
Not really, sir. We can go ahead with our next topic of this chapter.
Okay. Now, once we have seen these relations, another important concept actually we are going to observe. In fact, we have already seen a concept called Euclidean division algorithm for numbers. We have already seen this result for real numbers actually. Now the question comes whether such type of relations also holds true for polynomials or not. In fact, polynomials are actually generalized expression for real numbers. I already told that every number is also a polynomial, and some expression which are not numbers also gives a polynomial. So polynomials can be considered as a generalized expression from generalization of numbers to some notion by using unknown variable x. So that's why if something is holds true for numbers, we are trying to apply the same thing for the polynomials also. One such relation what we are going to take is Euclidean division algorithm.
Yes, there is a question related to this, sir, that can Euclid's division lemma holds for polynomials also?
Yes, that's the important thing we have to observe now actually. Again, whatever the conditions we are putting on the numbers, by handling these polynomials also as a nomial. Maybe in the class 9, they might have already seen how to divide two polynomials and how to find out the corresponding quotient, dividend, all those things actually. By using all those same concepts, here we are going to make a statement about Euclid division lemma with respect to polynomials also. That statement I am going to give it actually now. The statement comes like this. If p of x and g of x are any two polynomials, of course with g of x is not equal to 0 because we are dividing by this polynomial. Therefore, dividing by 0 is not allowed in mathematics. That's why we are putting that condition. G of x is not equal to 0. Then we can find two polynomials, say q of x, which we call it as a quotient of that polynomial, and r of x, which we call it as a remainder of the division, such that p of x is equal to g of x times q of x plus r of x, where r of x is either 0. If the remainder is 0, then we say that this g of x is exactly divides that polynomial. If the remainder is not 0, then it's satisfying the condition that degree of r of x must be less than the degree of the given polynomial g of x. This statement actually we are calling it as division algorithm for polynomials. In fact, it exactly holds true by using same division what we are going to do as numbers, even polynomials also we can do.
But what are its applications to polynomials, sir?
Yeah, it's a very good question, madam. In fact, every time we are trying to find the solutions. For
Yes.
linear equation, there is no problem. Easily we can find out. For quadratic equation, also certain methods they are mentioned in our lower level class. Now the question comes, once we introduce a polynomials of higher degree, for example, cubic polynomial, how to find its solutions? That's a very big thing that they never studied the solution for that type of. But here, by using this division algorithm, we are going to identify the roots of such higher degree polynomials if some roots are given in that case. For example, let us see one example with respect to that situation. Actually. In fact, in general, I am making a statement actually for that one. In the last slide, we will see that dividend can be written as divisor into quotient plus remainder. This is the statement actually we call it as division algorithm for polynomials. Let us illustrate this with an example actually. Of course, it actually an application for that one. Suppose there is a polynomial is given x cube minus 13x square plus 52x minus 60. We don't know what are the roots of this polynomial. In this problem, given that 2 is 1 0 of that cubic polynomial. If 1 0 is given, then how can you find the other 2 zeros? This is one very nice thing. We can use it by using that particular division concept. Now, let us see how it is possible. So, consider the given polynomial p of x is equal to x cube minus 13x square plus 52x minus 60. Now it is given that 2 is a 0 of that polynomial, then by using our 9th class knowledge, if some 0 is there, then the corresponding linear term x minus 2 acts as a factor of that polynomial. This is the result what we call as the factor theorem in the 9th class actually. Whenever we have a 0, by using that 0 as a number, we can construct a factor like x minus 2. So if 2 is a 0 of the polynomial, then it is known that x minus 2 acts as a factor of the polynomial. So once it is a factor means, let us see how it looks like by division. Now we are dividing x minus 2 by using a long division process. This also they learn in their high school level classes actually. By applying long division method, here we are going to divide our given polynomial by the linear term x minus 2. In that case, first they are going to multiply by x square so that we can cancel the x cube term. Then they are going to multiply by 11x so that they can cancel minus 11x square term. And finally, they are multiplying by 30 so that we can cancel all the term. Exactly the remainder is 0. When the remainder is 0, which indicates that x minus 2 acts as a factor. And whatever the quotient comes, that also acts as a factor for the given polynomial. That means our polynomial can be written as product of these two factors. One factor is the linear equation that is given x minus 2. Another factor is a quadratic polynomial that is x square minus 11x plus 30. Now by using our previous knowledge how to handle the quadratic polynomial, by using splitting the middle term, we can write that second term as x square minus 5x minus 6x plus 30. And again by splitting the terms, by taking the common factor from the first two terms as x, I will get x minus 5. Similarly, by taking the minus 6 as a common factor from the second two terms, again I will leave as x minus 5. That shows that that entire 4 terms can be split as 2 terms. One term is x minus 5 and another term is x minus 6. If they go on doing the factors very easily, then these terms become very comfortable for them actually. That shows that our polynomial p of x can be written as product of 3 terms x minus 2, x minus 5, x minus 6. That shows that the other 2 zeros of this polynomial are 5 and 6. In this way, we can identify the roots of other given polynomials. Okay. These are the interesting things we can always observe. And here, for example, I would like to discuss one more interesting problem, which may be slightly, it is for gifted students, because normally we cannot find out the solutions directly. Suppose you take the cubic polynomial. Here the problem is find only one real root. In the last problem, one root is given, we identified other 2 roots. Here the problem is something different. Just find out one real root of the given cubic polynomial x cube minus 3x square minus 3x minus 1. This is a very interesting problem. It's a challenging for our students also. That's why I want to discuss this with students, this problem actually. In fact, this involves only the basic concept what they studied in the lower level class. That's why I thought that it's very interesting. Here
yes, the students are even asking if you can explain the division algorithm polynomial problem again. But I think with these examples, they will understand automatically.
Yes. Okay. So, in fact, if you observe this polynomial, definitely 1 is not a root, because if you put x is equal to 1, the expression cannot be equal to 0. Therefore, even if you put -1, the expression cannot be equal to 0. Even if you put -2 or 2 or 3 or -3, in general, any integer if you put, this equation not equal to 0. That means no integer is a solution for this equation. And surprisingly, if you put any fraction, any real, any rational number, then also we cannot find a solution for this equation. That's the beauty of this equation. That means one real root of this equation may come as an irrational number. How to find that root? For that, we are using one simple trick which may help us to see the roots very easily actually. Let us start to see the solutions of that equation one by one. So consider the given polynomial x cube minus 3x square minus 3x minus 1 is equal to 0. What is the trick we are going to do is, we are trying to apply the completing the cube technique actually. Normally we are using completing the square technique. Here we are going to apply the completing the cube technique. So what I did is, whatever the minus terms are there, those minus terms I took it on the left hand side. Therefore the expression becomes x cube is equal to 3x square plus 3x plus 1. Now I am going to add x cube on both sides. So it becomes x cube plus x cube is equal to x cube plus 3x square plus 3x plus 1. So x cube plus x cube becomes 2x cube, very easily you can observe. And surprisingly, on the right hand side, whatever the expression you have, that exactly becomes x plus 1 whole cube. Because if they apply cubic formula, a plus b whole cube formula, a plus b whole cube formula is a cube plus 3a square b plus 3ab square plus b cube. Here a is equal to x and b is equal to 1. If you substitute those values, we are simplifying the right hand term very easily as x cube plus 3x square plus 3x plus 1 can be expressed as x plus 1 whole cube. This is the first thing we have to do. Now once you see the term, I want x actually from that equation as one real root. Therefore to find the x, I try to remove the cube power. For that, the simplest trick is again by taking the cube root on both sides. So if you apply cube roots on both sides, x cube whole cube root means it becomes x, and 2 is there, therefore it becomes cube root of 2. Therefore the left hand term becomes cube root of 2 into x. And right hand side x plus 1 whole cube is there. If I apply cube root, whole cube gets cancelled, we left with x plus 1 only. Therefore the expression becomes, by taking x on the left hand side, cube root of 2x minus x is equal to 1. So by taking x as a common factor, we left with cube root of 2 minus 1 times x is equal to 1, and therefore x is equal to 1 divided by cube root of 2 minus 1. But normally the notion is, whenever we have an irrational number in the denominator, we never keep it as it is. This is the practice in our irrational factors actually. That's why whenever we have irrational number in the denominator, we always apply one important technique called rationalizing the denominator. That means we have to find out one term such that if you multiply and divide by that term, the denominator becomes free from roots. For example, for this, I am going to use the formula a cube minus b cube is equal to a minus b times a square plus ab plus b square. This formula, I think in the class 6 or 7, they already learned, our students. Now I am going to apply this formula. I have a minus b by taking a is equal to cube root of 2 and b is equal to 1. So my a minus b term is already there. Now I want to clear it, and it can be written as a cube minus b cube means in the second factor, a square plus ab plus b square is there. Now I am going to multiply this factor and divide by this factor of that equation. We will see what happened. Some magic happened actually that we are going to observe. So the expression is x is equal to 1 by cube root of 2 minus 1. For this term, we are multiplying divide by this particular thing where a is equal to cube root of 2 and b is equal to 1. It becomes cube root of 2 whole square plus cube root of 2 into 1, that is nothing but cube root of 2 plus 1 square means 1. Same thing you have to divide by that one also. If you do like that, what happened is one magic happened, particularly in the denominator. Let us observe what happened in the denominator. In the denominator, the entire expression looks like a cube minus b cube, where a is equal to cube root of 2 whole cube and b is equal to 1 whole cube. Therefore, the numerator becomes cube root of 4 plus cube root of 2 plus 1. Denominator becomes cube root of 2 whole cube minus 1 cube. But cube root of 2 whole cube means 2 and 1 cube means 1. Therefore, 2 minus 1 becomes 1. So, entire denominator becomes very clear. Now, we are getting an irrational number on the numerator, which is very comfortable for handling the term. Therefore, finally, we are going to get a term x is equal to cube root of 4 plus cube root of 2 plus 1. This is the one real root of that particular polynomial. I think our students can enjoy by applying all those things and find that particular term very easy.
If you want to suggest some examples or exercises for our students from the book, if they can do it.
Okay, in fact, in the books, there are lots of equations are there, but my suggestion is let them don't touch for cubic polynomials, because if they try to solve the cubic polynomials without the knowledge of how to solve those techniques, it is very difficult for them to find the answer. But for a given polynomial, if the sum of the roots and product of the roots and sum of the product of the roots, particularly for cubic polynomial, I'm telling, if these three things are given, then they can always find the corresponding polynomial, even for cubic polynomial also, very easily by applying the same technique as we did it for the quadratic polynomials. Such type of problems are all there in the exercise. Let them go through those problems and definitely they will enjoy by solving all those things.
And of course, maths is all about practice. If you can do a recap of the next session, what all is left in polynomials and what we'll be discussing in our coming sessions.
Okay. In fact, we may find out some more problems on the division of the polynomial that I have not done it actually. I thought that they already saw the division of a polynomial by another polynomial. So what I thought is, suppose if we have two different types of polynomial, one is of higher degree, another one is lower degree. In that case, how the division happen, how the division algorithm looks like exactly, how to get the factors, and how to find the corresponding remainder in the division. All those concepts I just postponed it for our next class.
Perfect, sir. Because already whatever we have learned, students, you can go to this video again in our official YouTube channel, NCERT official. You can watch this whole session again. You can watch our previous sessions as well to do a quick revision of whatever has been taught till now and practice that. Thank you so much, Prasad sir, for joining us.
Thank you. Thank you very much.
And we will look forward with more such sessions with you. And students, do your revision and wait for the next session. Thank you so much, everyone, for watching us. That's all for this session. After a short break, we'll talk about concept of shapes for our primary classes for class 2. That's it for now. Namaskar.
Namaskar.